Good morning, everyone. Myself Devika, working as assistant professor in the Department of Electrical and Electronics Engineering at Srinathkumar Institute of Technology. Today we have discussed the subject on MR3452 Control Systems Engineering for 2021 regulations. Today we have discussed the topics understanding transfer functions, determining the order of control systems, exploring stability concepts, that means critical, absolute, and relative, analyzing poles and zeros, methods for stability assessments, VIBO, stability explained, and characteristics of transient response. Transfer function. The plant's transfer function denoted as G of s. It is defined by the ratio of output Y of s to the input U of s. So we have to write G of s equal to Y of s equal divided by U of s. Then transfer function characteristics. It is classified as proper when the degree of its denominator polynomial exceeds that of the numerator. So the numerator degree is equal to or higher than the denominators. So the transfer function is considered improper. So a of s divided by x of s equal to b naught s power n plus b1 s power n minus 1 plus etc. till f bn. So divided by a naught s power n plus a1 s power n minus 1 plus etc. till an. This is the condition n greater than or equal to n. So this is improper. Then understanding stability. So we have to three concepts: stable, neutral, unstable. This one is stability by imaging a cone resting on a flat horizontal surface. This simple setup helps demonstrate the principle that determine whether an object remains steady or tips over. The transfer function overview. The transfer function serves as a tool to evaluate system stability, and it reveals both time domain and frequency domain behaviors of the system, and it predicts how the system will react to any specified input signals. Then stable systems. We know that the system is considered stable if every bounded input produces a bounded and controllable output. When no output is applied, the system's outputs gradually approach zero as time progresses. This is stable systems. The characteristics of stable system. A system is considered stable if every bounded input produces a bounded output. So stability depends on the position of the system's root in the complex plane. For a system to be stable, all roots must lie within a specific region, ensuring bounded responses. Then unstable system. A linear time invariant system is classified as unstable if when subjected to a bounded input, its output flows without the limit. So in other words, when the system receives any input, the output continuously accelerates, making it impossible for the designers to regulate or contain the response. Then critically stable system. When a linear time invariant system receives an input, a critically stable system's output neither grows without bound nor fades away to zero over time. Instead, the output typically oscillates within a limited range or settles at a constant level. These systems are considered neither stable since their response does not diminish to zero nor stable as their output does not increase indefinitely. Then, relative stability. A system can be deemed completely stable if it successfully meets the criteria of the route stability test. Consequently, its output diminishes to zero when no input is applied. The speed at which this output fades is crucial for understanding the idea of relative stability. So poles a position further left in the left half of S plane away from J imaginary axis cause the system response to diminish more rapidly. The greater the distance of these poles from imaginary axis, the higher the system's relative stability becomes. Comparing pole positions for stability. Visualizing the pole's location on the complex plane and system A and system B, each future pairs of complex conjugated poles. Then poles are marked at positions plus or minus j omega, that means imaginary, and shifted along the real axis plus or minus omega. System A and B differ in the placement of these poles, which influences their relative stability. Then understanding zeros in Laplace functions. Zeros are the specific values of the variable s that cause the Laplace function to equal 0. Essentially, these zeros correspond to the roots of the numerator polynomial in the function. For example, in the function fraction of 10 s 10, of, 10 into s plus 2 into s plus 1 into s plus 3, the zero occurs at s is equal to minus 2, z1 is equal to minus 2, z2 is equal to minus 1, z3 is equal to minus 3. These are the zeros. When zeros are complex numbers, they always come in pairs that are complex conjugates of each other. Then poles. Poles in the Laplace transform are specific values of s, where the function values becomes unbounded, essentially where it suits off to infinity. These poles correspond to the roots of the denominator polynomial in the Laplace expressions. For example, in the function fraction of 10 into s plus 2, s plus 1, s plus 3 has poles located at denominator. So p1 is equal to minus 2, p2 is equal to minus 1, p3 is equal to minus 3. When poles are complex numbers, they always come in pairs that are complex conjugates of each other. Then control system stability. The solution to the denominator polynomial of a transfer function are known as its poles. The solution to the numerator polynomial of transfer function are referred to as zeros. So poles are denoted as P1, like P1, P2, P3. Zeros are denoted as Z1, Z2, Z2, etc. So it marked in the graph poles into and zeros means circle. So the system poles are denoted by x, while its zeros are marked with 0. The order of the system corresponds directly to the total number of poles in its transfer function. Stability of control systems. A pole refers to the specific frequency where the system's response theoretically suits to infinity, which is why it is called a pole indicating a point of infinite magnitude. Conversely, a zero is the frequency at which the system's output drops to zero, effectively nullifying the response at that point. So poles and zeros of a transfer function correspond to the frequencies where the denominator and numerator of the function become zeros, respectively. These values play a crucial role in determining the system stability and overall performance. So stability. So system is stable if bounded inputs produce bounded outputs. Stable means if all poles lies in the left of the plane. Unstable means if any poles lies in the right of the S-plane. Marginally stable means one pole lies at origin and all other in left half of the S-plane. Sample problems. Analyze the following transfer functions. So assess if each transfer function is proper or improper. And then identify the system's poles and zeros. Then determine the system's order and sketch the pole zero diagram and evaluate the system's stability. So in this first one, g of s equal to s plus 3 divided by s into s plus 2. Here, poles is P1 is equal to 0, P2 is equal to minus 2. In zeros in this problem, z is equal to minus 3. Likewise, second and third one and fourth. Alternative perspective on stability. So the system is said to be stable for any bounded input. The output of the system is also known as bounded. Thus, for any bounded input, the output either remain constant or decrease with the time. So, bounded input, bounded output versus transfer function. For example, g1 of s equal to 1 divided by s plus 3. In this transfer function, we have to draw the pole zero map diagram. The poles are placed in the left half of the S plane. So the system is stable. Second one, G2 of S equal to 1 divided by S minus 3. So the poles are placed in the right half of the S plus S plane. So the system is unstable. Google stability was a transfer function characteristics. If any poles of the system lie in the right half of the complex plane, the solution to the system dynamic equations will include poles that grow exponentially over time. So stability concepts. So we know stability, the system's output remains within limits when the input is also limited. Asymptotic stability, when the input is removed, the system's output gradually diminishes to zero. Then critical stability, the output either oscillates within a fixed range or settles at a constant value. Absolute stability, the system stays stable for every possible set of parameter values, ensuring bounded output regardless of pole equations. Then transient response parameters. So settling time, peak time, rise time, delay time. So settling time means the duration required for the system output to remain within a specific percentage, commonly 2% or 5% of its final steady state value after a disturbance. Then peak time. And in this, the time at which the system's response reaches the maximum overshoot beyond the steady state value. Then rise time. The interval taken for the response to increase from 0% to 100% of the steady state value for the first time. Then delay time. The time elapsed before the response initially reaches a certain percentage, often 50% of the steady state value. These parameters are essentially for analyzing how quickly and accurately a system responds to changes. This is the transit response characteristics, delay time, 50% and rise time 100% time at the peak overshoot, settling time. Conclusion. Stability is a fundamental requirement for the reliable and secure operation of electrical systems. It ensures that the system can return to its normal operating condition after disturbance such as faults, load changes, or switching operations. Then different types of stability, proper design control strategies. With increasing integration of renewable energy and modern grids, advanced stability and these methods are becoming more important. These are the reference of these topics. Thank you.